Hello, we are team number 18, otherwise known as KAIKANA. This is our spring 2022 presentation for EEE 489. My name is Victor Escarate-Cruz. Our project's purpose was to design a power solution for NASA's hypothesized surface explorer mission to the asteroid known as Psyche 16. We ultimately chose a battery-powered solution, mainly because of its feasibility in terms of powering our components, and also because of its resistivity to cold temperatures, which is abundant in space. We can see from the diagram on the left that we have a variety of components that we are powering with our battery, including power converters, an optocoupler, Arduinos, and sensors. Each teammate has been designated with a specific task. Jonathan Hawkins has been tasked with the creation and the analysis of the circuit board, as well through manipulating the power structure in our system. This is so that the components are not overloaded with power. This is through the use of the buck converter and the optocoupler, which were both designed by him. Robert Smith is in charge of the thermal controls and the data acquisition. This is so that our project system is maintained at a stable internal temperature, and as well as reading our data in real time through a program called ThinkSpeak using a Wi-Fi module. Shaun Caldwell is in charge of Arduino programming, and through these programs he will make sure that the Arduinos can accurately connect with the sensors and read back in our data. Finally, Victor Escarate has been tasked with our project's final components assembly, as well as our real-world testing for our demonstration. Now I will hand it over to Jonathan Hawkins so he can talk about the power electronics.
Thanks, Vic. I am Jonathan Hawkins. I designed the power electronics side of the Hypothesized lander. While constructing the components, multiple issues were found via supplying components from the PCBs we designed. We utilized EasyEDA JLPCB to construct the components. As shown in the photo on the right, the circuit is what we contrived and ran into the issues of inventory shortage. The primary distributed energy resource will be supplied via the battery, which is a 3 amp hour 12 volt battery. It is used during our initial testing and will be used as the final results to keep our results similar. We implemented 2 buck converter components for each voltage demand. LEDs were installed through troubleshooting efforts. Voltage will input the connection side and split in 2 directions supplying each buck converter. Each converter will step down voltage via their linear regulators respectively. The additional components filter any unnecessary spikes in respect to their component output. The first voltage regulator supplies 9 volts to Arduinos via the conductors through the barrel connectors that I've soldered to maintain the integrity of the components from the conductors on the board. The 5 volt buck converter will supply potential to the optocoupler and the components once connected. The optocoupler will act as a solid state to be activated from the input signal from the Arduino Duos. The recommended conductors supplying the voltage and current from energy sources are THWN 12 gauge as the current draw and from the battery. The peak amperage at 12 volts would reach close to 2.25 amps. If the conductors are running approximately 1 meter from the resistance would be 20.92 milliohms, and the voltage drop would be minimal at 47 millivolts. The conductors supplying the instruments and controllers utilize an 18 gauge as peak rated amperage is 14 amps in accordance with the NEC table 310.16. 18 gauge used for sprinkler wireless systems, and the cost to repair will match the convenience. As I now pass this to my colleague, Robert Smith.
Thank you, Jonathan. Let's go over a quick review of a thermal controller. Why do we need feedback? The lander in extreme conditions requires added heat equal to its loss to maintain stable operating temperatures. The lander's loss is considered through the second law of thermodynamics, which states that when a path of conduction or radiation is made available, heat flows from the hotter to the colder body. In the vacuum of space, heat loss is due to radiation. For our demonstration, the lander's environment will be inside a freezer, thus convection from surrounding air will also be added to its loss. This leads us to the controller for our demonstration. Our controller requirement is to maintain 32 Fahrenheit and sub-zero freezing temperatures. Due to material lead times and budgeting constraints, our system will now use a digital relay for turning on the heating element. The SD card is replaced with a Wi-Fi shield for wireless streaming to the cloud for real-time data analysis. There will be 2 controllers, one for environment sensors, which my colleague Shaun will be discussing, and one for thermal control and data transmission. Our final build for the thermal controller will include an Arduino Duo that will utilize an RTD to sense the conductive heat given from the polyamide heating film. This heating element will be controlled by a relay to switch on if the temperature is below a preset temperature. Aluminum foil will be used as a heatsink to our components. The heat transferred through the aluminum foil will be sensed using a TMP36 sensor. This will be soldered to a small PCB for placement on the aluminum foil. Due to the sensitivity of the transistor, a low-pass Butterworth filter is used to smoothen the variance in readings. Using comparative logic within Simulink, our controller can switch the relay on if the difference between preset and detected temperature is greater than 0. Testing and simulation while using a thermal camera showed that our system works. We noticed an initial 6% overshoot during startup of the heater with a rise time of 35 seconds, after which the RTD was able to control the heating output and maintain the set temperature. Simulink allows for the Arduino to connect through a Wi-Fi shield and distribute that data wirelessly through a live channel using ThinkSpeak. We can broadcast 4 streams of data and use MATLAB to present a visualization of the incoming live stream through a web address. These streams include a Gauss meter, surface temp, distance from the surface, and operating temp. Our team would like to invite our viewers to see this data in real time during demo day. And now my colleague Shaun will continue with the sensor data acquisition from the lander's environment.
Thanks, Robert. As explained earlier, we will be using multiple Arduino Duos to acquire and analyze the data received through our sensors. We are running programs through Simulink as well as the Arduino Integrated Development Environment, and have written and modified hundreds of lines of code to fit our needs and to present our data in an uncomplicated manner. We have 3 of the sensors, the temperature, distance, and magnetic field, which are running through one board, and they send an analog signal to another board which can transmit the data so we can read it off-site. To measure the magnetic field of Psyche, we chose a 3D magnetic Hall sensor produced by Infineon Technology. This device uses very little power and takes measurements in the X, Y, and Z directions, which we will use to find the magnitude of the magnetic field. Programming of this device was the most difficult, as it has multiple power stages which need to be chosen to even access data, so we used and modified an existing program written by Infineon, which is available to the public. This device also has a very good range between 0 and 160 millitesla, and enough resolution to read in 5 microtesla increments. To measure distance, we went with an optical sensor by Sharp, which measures between 3 and 31 centimeters. We want to measure surface to lander distance as our machine descends to Psyche, so we can compare data with the magnetic field. With our budget being so tight, we chose this sensor to show the workings of our final design, but in reality, we would go with a sensor with a range of at least 100 meters to give us a much broader comparison. For temperature, we are using an Omron D6T thermal sensor, and that ranges from -30 to 40 degrees Celsius, which is very adequate range, but again, we have chosen this sensor due to our low budget. The surface temperature of Psyche is believed to range between -215 and -20 degrees Celsius, so our sensor would only be accurate on the hotter days. There are products out there like platinum thermocouplers, which can measure much lower temperatures, down to -300 Celsius, but they go for hundreds to thousands of dollars. This was Shaun Caldwell, and next, Victor will talk about our final design. Thank you.
Thank you very much, Shaun. My name is Victor Escarate-Cruz once again, and I wanted to speak on the final component assembly and the base of our model. We have obtained a 2x4 foot base, which will house all of our electrical components on top. Originally, we went with a design as seen to the left of our Tinkercad model, which houses a variety of our components. This will be easier on a wooden plywood base, because it will also balance our battery and it will have a close proximity of most of our electrical components. Then we will wire together our components using a soldering technique. This will make sure that most of the power is attached to one another and our components are in synchronization. We all have the same power load. After that, I will finish the programming on Arduinos. I will finalize the sensors in order to make sure that they are accurate and working and taking in data. And once all of our components are together and assembled in a system and we are ready to start testing, we will begin so. We have obtained an industrial freezer setting in order to model the effects of outer space and the temperatures of outer space, since this rover is supposed to land in Psyche 16 in the asteroid belt. We will place our project in the industrial freezer and take in the data in real time, upload it to ThinkSpeak so all of our team members can view the data. Since the foundations of our project in the fall of 2021, we have made considerable amounts of changes to our project's design, the most significant of which have occurred recently in the beginning phases of construction of our project. One of these major changes is the method of data acquisition. Originally, our plan was to have data be written onto a microSD card and later read after testing. However, thanks to Robert Smith's expertise in Simulink and MATLAB, we will now be using a program that uses IoT technology in the cloud to upload real-time data into this channel. The channel can be read in demonstration purposes, but also between our teammates, so we have real-time data to discover. We also had major changes because of financial limitations. Most significantly, we had an enclosure model, a cube-shaped construction made of plexiglass with drawings on top of it, that had to be scrapped because of financial constraints. This was replaced by the baseboard previously discussed. Our budget had been reduced by over 1,000% throughout the course of this semester. And because of this, we had to scale back on our constructions and our materials, and now we simply have our components that are necessary for our testing later on. We've also made changes to our demonstration day. This is also tying in with our budget constraints and the fact that we could not afford a vacuum in order to really simulate the effects of space. Instead, we will simply be simulating the cold temperatures of space using an industrial freezer rather than a vacuum itself. Thank you very much for your time.